Since the spring mass is the simplest and most basic oscillator, it's a good place to start. But you need to understand that this part, this discussion, is the mathy discussion. After we do this derivation, you just need to memorize a couple of basic things, and you can do most simple harmonic motion problems. Most simple harmonic motion problems are tacked on to something we've already done. For example, the problem you did for your test, where the rod was pulled sideways and then released and struck the ball, right? That problem exists dozens of times in the AP literature, but in many of those AP literatures, the bar doesn't stop, it swings afterwards, and the very next question would be, what would be the period of oscillation of the bar? Most of the time, simple harmonic motion is merely tacked on to a portion of an FRQ. So us spending 4 or 5 days or less on this is okay by me, but this math, this is for when it's not just tacked on. And your homework's gonna have 3 of these examples, which are the most basic examples that are likely to show up on the exam. So here we go. A simple harmonic oscillator, and we're talking about a spring mass simple harmonic oscillator, consists of a spring and something with inertia. And to make this as simple as possible, we're going to assume that there is no friction in the system, no air resistance in the system. All we have is a object of mass m and a spring constant of spring constant k, currently in the equilibrium position, so there are no forces acting on the system. Okay? Now I want you to consider what would happen if I were to take that mass and pull it out to the right a small amount. I mean, the obvious thing is that it would stretch the spring. So I have pulled the system out a distance, and I'm going to call this x naught for the time being. Now, this part's going to be tough, so I want you to imagine this is the instant I pull it out and let go. So I'm no longer holding it, but I've frozen that moment in time, and I'm saying that this moment is t equals 0. Okay? So I've just released it, and I'm saying that this moment is t equals 0. Everybody okay? Now, at this instant, where's the energy? It's in the spring. What kind of energy did we call that? Energy in a spring. Elastic potential. So right now, this system has elastic potential energy equal to 1/2 k x naught squared. All the energy is there. Now, for a moment, this object is at a displacement of x naught. So at this moment, there is a force acting on the mass. What is the direction of that force? Is it this way or this way? All right, so back towards where it came from. True? When I first introduced Hooke's law, I said that it was called a restoring force. Here, that's what I mean. There is a force that is attempting to pull the box back to where it started. That's why it's a restoring force. So I'm going to make this the positive direction. And I'm going to state that the only force acting on the system is the Hooke's law restoring force. There's a negative sign in this equation on purpose. Hooke's law always has an explicit negative sign. It's to remind you that the direction of this force is in opposition to its displacement. That's a big sentence, and I'm willing to be patient. The direction of this force is in opposition to its displacement. So if I had pushed the box in first and let it go, do you realize the direction of this force would be to the right instead? Because my displacement would have been negative, and therefore my force would have been positive. So the restoring force always opposes the displacement. That's essential. That creates what's called an energy well. an important piece of knowledge for our next and last unit. Now, I want to advance this to another instant in the future. So that didn't work out exactly how I wanted. So I'll do it this way. So there exists a moment in the future where the box has moved a little bit to the side, but is not yet at equilibrium. The spring is starting to give the object a little velocity, but we are still located a distance x away from the equilibrium position. There is elastic potential energy now. Because we're not at equilibrium, there is a value for x. But we're moving, so there's kinetic energy too. But as there was no work done by friction, these two have to add up to equal the original amount of energy in the system. Point number 2 about simple harmonic oscillators. Yeah, it's about physical parameters that control the period. They conserve energy. So simple harmonic oscillators are exercises in energy conservation. The energy of an oscillator is based on its amplitude. At this moment, the object is still experiencing a force. And that force is based on Hooke's law, but that force has gotten smaller because we are closer to equilibrium. Eventually, we're going to make it back to where we started. So let me just move these. Oops. I'm just going to move these over here. Oh, Mr. Shelton. Just make it. Just do the thing. You go over there. You come down here. There. I know you guys have to redraw it all. You redraw it all. I'm not. I have to be faster. So we reach this point where we are back at equilibrium. We're no longer displaced, so x equals 0 right now. We are at equilibrium. But this sucker's probably moving, right? Still moving to the left. It has a velocity now. Since x is 0, there is no elastic potential energy now. The only energy we have is kinetic energy. So all the energy is in the form of kinetic, which means we are traveling at our fastest. When we travel through equilibrium, we are at the maximum speed. When we travel through equilibrium, we are at the maximum speed. In fact, we know what that maximum is. 1/2 mv max squared has to be equal to 1/2 k x naught squared. That relationship has to exist because it's still a conservation of energy relationship. But at this moment, net force equals 0. Now, I need you to understand, I've told you everything that you need to memorize about an oscillator in these 3 steps. Because this system just repeats itself now, right? It passes through this point, keeps going to the left until the spring stops it. And then it comes back, and the system just keeps going back and forth. It's an exchange of energy. Energy is constantly moving between kinetic and potential. This represents 1/4 of the movement. This is 1/4 of the movement. Eventually, we'll make it back to this position. but we are only 1/4 of the way there. So this is 1/4 of the period. We pass this point, we'll travel to x naught on the other side and stop, and then come back. Now, need to add a little bit to this, not much, just a little bit. Net force equals ma. At this instant, the very beginning, minus kx naught equals ma max. At the extreme, we have 0 velocity, but maximum acceleration. Right? The velocity is 0 here. We released it. So v equals 0, but we have maximum acceleration. Right? Because we're at maximum displacement. Here, we're mixed. We have velocity and we have an acceleration, but we're somewhere in the middle. Here, net force equals 0. That means acceleration equals 0. It does not accelerate at the instant it's passing through equilibrium, but velocity is at a maximum. This is unlike any other motion we've talked about this year. The acceleration isn't constant, the velocity isn't constant, and the displacement isn't constant. So there are no motion equations that we know of that satisfy this. Because none of these things are constant the way that we're used to. The acceleration is always changing. So I want to stop right now. I want you to understand that these are the basic parts. In fact, I am going to post a simple worksheet that shows one complete half-period motion. I would go through and just label it with all this information. Every oscillator does this, every one of them. So whether it's a spring mass, a pendulum swinging, a torsion pendulum, every one of them does this in one way or another, but it's always an exchange of potential energy for kinetic energy. Always. Some form of potential energy and some form of kinetic energy. It's always an exchange for velocity and acceleration and displacement. Always. And it always obeys this pattern. So I want to just look at one of these for just a moment. I want to look at the one that's in the middle. And so I'm going to take all this distraction off the board and just talk about what's going on in the middle. I'm considering this moment that's just in the middle somewhere. It's got some velocity, but it is some distance away from equilibrium. You have to be able to tell me what controls the motion of the system, which means you have to come up with a motion equation for this system. I want to show you how this is done, and I want to show you the parts you're responsible for and the parts that you're not responsible for. To create a motion equation, if you recall, we start by trying to find the acceleration. And then from the acceleration or the displacement, we can go one way or the other because we know that the acceleration is the derivative of the velocity and the velocity is the derivative of the position. So if we can get one of these functions, we can derive the other two. Does that sound familiar from first semester? So just a reminder, acceleration is dv dt. And velocity is dx dt. So if I can get one of these functions, I can generate the others. That means we need to find some kind of function that has something to do with t. So here's the sentence that you're going to hear on the test. Write, but do not solve a differential equation that could be used to find something as a function of t. In this example, we're going to find position as a function of time. So this question sounds familiar to you all, right? Do you remember where you start? If not, I'll help you. There's only two places to start, and the only one we've ever done has been to start with Newton's second law. because it has a derivative built in. So that's where I want you to start. Newton's second law. This is a net force equals ma problem. Now we have to add up all the forces and set them equal to ma. There's only one force, the force from the spring. So the force from the spring is minus kx, and that equals ma. Now, when we've done differential equations before, we've said that the next step is to put a derivative in for one of our variables. We have a derivative for a. The problem is that derivative doesn't give us a function with x in it. It gives us a function with v in it. So we would not be able to solve this differential equation unless we had v over here someplace, and we do not. But you guys are smart, learned people. You remember that v is also a derivative. So we're going to put in the derivative twice. We're going to replace a with dv dt, but now we're going to replace v. Two substitutions. What we're doing right now, you will probably never have to do. Probably. But when I'm done, I'm expecting that you can, because it could come up. It's probably only going to be worth 1 point. But you have right now the derivative of a derivative here. Now, that's not a big deal in that you've done this already in our class. You've taken the derivative of a function twice. You've been given position and taken the derivative and found velocity, and then got the new function and taken the derivative and found acceleration. You have done that way back in September. That's all this is telling you to do, is get your function for x and take the derivative twice. That's all that says. But here's the weird part about this. If I do the next step that you were told to do in solving a differential equation, which was to isolate the derivative, you would have to isolate it by getting it by itself. This was the next step. I said, if we're going to solve one of these, you isolate the derivative, and then we split the derivative. Well, this is going to be minus k over m times x. There is no easy way to say this, but you can't split this derivative because there's two of them. Now, you guys who are in calculus, you may have seen this notation already. There's a way that you're supposed to write this. Do you notice how it's like a d times a d on the top? So they'll write that as d squared x. And do you see how it's like dt times dt on the bottom? They'll write that as dt squared. Don't get too hung up on this, but this is the symbology that's used. This is called a second order differential equation. Second order means you take the derivative twice. Now, we will run out of time here, but you guys who have had calculus already, you can read this in a way that people who haven't had calculus can't. So you guys who haven't had calculus, I'm going to help you read this. This says, if you have x as a function of t. Now, we've seen x as a function of t before, right? Let me just show you one. That's x as a function of t. Do you remember that from first semester? This says, if you have x as a function of t, and you take the derivative twice, you will get back the original function. That's what it says. Times a constant. Now, you guys in calculus, name a function that when you take the derivative, you get back the original function. E to the x. Now, we know that if you have, say, x naught e to the t power, if this is my function for x, and I take I'm speaking to calculus, and I take the first derivative, I'll get dx dt equals x naught e to the t. Well, if I take the next derivative, I'll get x naught e to the t. Now it works. The second derivative gives me back my original function, but it also has to pop out a constant. So if I put a little constant here, the first derivative will pop out a c. And if I take the second derivative, I'll have a c squared. That's how the second derivative would work. And folks who haven't had calculus, you should be able to follow this. We've done this in this class. Here's the problem. I also need to pop out a negative sign. If I take the first derivative, I don't get a negative sign. If I put a negative here, will I get a negative sign? People who have taken calculus know that'll pop out a negative sign, sure. But if I take the next derivative, it'll cancel out that negative. What we are trying to do here, for those of you who have never done this before, is we're trying to do differential equations without having differential equations as a class. This is called guessing a solution, and is an actual process that is done in differential equations. Chapter 1, guess a solution that will fit the differential equation. This doesn't fit because it doesn't work. We need something that when we take the second derivative creates a negative sign. Everybody in calculus knows the answer. What's the answer? I'm listening, calculus folks. Sine or cosine. If you've taken calculus, you know why. If you haven't taken calculus, you're about to learn. And yes, I expect you to know this. We need this for this function. So you need to learn this, and you're going to learn it right now. Well, that sounded like it had authority behind it. Thank you. It's just Sergio? Glad you can make it, Sergio. Sergio's not really in this class. He just chills in here. But I want to take this derivative. You need to know how this works. I've made a basic function for sine. I understand that in pre-calc you guys are doing trig function graphing. So this should be something you're aware of.
Club Day, and today is Orange Club Day. Teachers, please allow students with Orange Club cards to report to the club meetings at this time. Students must have a club card to be admitted to the hallway. No other students should be allowed at this time. Thank you.
You're not leaving until you at least write these down. The derivative of sine is cosine. But because there's a constant in here, this constant pops out front. I need you to know this and commit it to memory. It's on your equation sheet. The derivative of cosine is minus sine. But again, there's a constant in there, so it pops the constant out. I need you to know this because we're going to finish this Monday, and you will need to know how to use this. My expectation is that you already know how to graph this and what this function looks like. Okay? All right.